All right, Math 2, Unit 6, indirect measurement. So I like these problems because the problems are kind of goofy, but they show you how it could be used in real life if you wanted to. And I know some people who have actually used this in real life to find how tall different trees are in their yard. So this is something that can actually be used, and it is correct. So we'll see. Number one, this is a shadow problem. So a 14-foot tall giraffe stands next to a globe, and we don't care that it's standing next to a globe right now. A 14-foot tall giraffe casts a 7-foot shadow. So we've got our giraffe there. I know it's a very detailed giraffe. It's 14 foot tall, and it casts a 7-foot shadow. The globe is 2 feet tall. How long is its shadow? So over here we've got the globe. It's 2 feet tall, and we have its shadow. We're going to call it x. Now here we could imagine that the people are standing up at right angles, because hopefully they're not slouching. And then we've got our sun up here. Let me do that in orange because that's a sun color. We got our sun up there, and really we would have that. Those are like the sunbeams coming down. That's really ugly. There, maybe that's a little bit better. There's the sunbeam coming down. Now we can think about the sun being so far away that the angle of elevation, this angle down here, would be congruent, right? So we assume that the people are the giraffe and the globe are standing up at right angles, which most people who stand up do normally stand up at a right angle. And the angle of elevation, and that's probably a new word for you, but the blue angles there, the angle that the sun ray and the ground make, those would be congruent because the sun is so far away that those angles would be the same. So we have two angles listed here. So we have angle-angle similarity. And we're going to use that idea. We're going to use the idea of similar triangles to solve this problem. So this is just like, I think, the last two problems on the last homework assignment, or the last notes. So we want to find x here. I'm going to put x in the numerator. And again, the x in the numerator, I just think helps. It makes it a little bit easier to solve. You don't have to do it that way. The x can go in the denominator, but I think it's useful to put it in the numerator. My x and my 7 correspond. My 2 and my 14 correspond. So I'm going to say x over 7 equals 2 over 14. And the reason I can say this is because I know that they are similar triangles. I know that they are proportional. So I solve here. I get x equals 2 times 7 over 14, which is actually 1. So x equals 1 foot. And by reading the problem, we probably could have noticed that because the 7 is half of 14, 1 is half of 2. But some of the problems, it's not necessarily as easy to see. All right, number 2. A 6-foot tall baby giraffe is standing next to a lawn ornament and casts a 15-foot shadow. So again, the wordings of these problems are sometimes kind of wonky. We don't care that it's standing next to a lawn ornament right now. We just care that it casts a 15-foot shadow. So we have our baby giraffe. We have a 15-foot long shadow. So here's 6, here's 15. We say the lawn ornament casts a shadow that's 10 feet long. How tall is it? So again, we have our triangles here. We know that these angles here would be the same because they have the sun rays there, and that these angles would be the same because they're standing upright. So again, we're going to write our fractions. I'm going to start off with my x, and x would correspond with 6, and then 10 would correspond with 15. So to solve this, I'm going to multiply by 6, and I'm going to get x equals, let me change these colors to the blue. X equals 10 times 6 over 15, which is the same thing as, 10 over 15 is 2 over 3 times 6. The 6 and the 3 can reduce to 2 times 2, which is 4. So I guess I should say 4 foot. There we are. All right. So these two problems are shadow problems. They're going to be done almost the same every single time. You're going to draw your triangle, you're going to fill in the blanks, and it'll either be the height or the shadow that is missing. Number 3, this one's a model problem. So a plane is 16 feet tall. A model of it was built with a scale of 1 inch to 4 feet. How tall is the model? Now, there's a few different ways to do this. I like to draw a little bit of a picture for me to see. I don't know, that helps me. So a plane is 16 feet tall. We'll put our 16 here just to stick to be how tall they are. A model was built at a scale of 1 inch to 4 feet. Now, what I normally do with these problems, and I know there's other ways to do them, but this is just the way that I do them. So 16, and I'm going to have my model there as x. And then on the right side for my other kind of shape, I'm going to put these guys there, the scale factor. It's going to have 4 and 1, 4 to 1. And to me, this just kind of helps me to see what I'm dealing with. Another way that helps me to do these is if I list down that this is feet, this is inches, this is feet, this is inches, kind of to show me what's happening here. Normally with these problems, what I do is I like to have my inches in one fraction and my feet in another fraction. You don't have to do it that way. That's just the way that I like to do it. There's all kinds of different ways that you could write these proportions that would be correct. So I'm going to start off with my x over 1, and then I go back to the left side there, 16 over 4. So this ends up just being x equals 4, and we're dealing with inches, right, because x is in inches. All right, let's do another one of these. A statue is 15 feet tall. So here's our statue, 15, and this is feet. A model was built at a scale of 1 inch to 3 feet. So we've got a model here. It's x, and it is listed in inches. And then our scale factor goes over here. We have, again, feet and inches. It is 3 feet to 1 inch. So again, I'm setting it up very similar to the other one. I'll start off with my x on top. X inches over 1 inch is 15 feet over 3 feet. So x equals 5. Last year I found that the problem that most people struggle on are like number 3 and 4, the model problems. So if you have trouble with those, please shoot me an email and I can help you with those. All right, let's look at number 5. Now these are map problems. They can be done pretty similar to the model problems. I just normally write them just a little bit differently. So Santa Cruz and Milton are 24 miles from each other. How far apart would the cities be on a map? So whenever I think of a map, I think of left to right. I don't know why I do that, but that's what I do. So I'm going to say Santa Cruz and Milton, they are 24 miles apart. And we want to know how long would they be on a map, and it is x inches apart. And then again, I go to the right and I say, well, we've got 4 miles to 1 inch. Now what I'm doing here is the same thing as what I did in number 3 and 4, but I'm writing it horizontal, and I don't know why I like to do that, but to me the maps make a whole lot more sense if I think about them left to right. You could definitely make them north to south if you wanted to. It really doesn't matter. But the two different types of problems here, the model problems and the map problems, are very similar. All right, so I will take, to write my proportion, I'm going to take x inches over 1 inch equals 24 miles over 4 miles. So I just reduced that, and x equals, what's that going to be, 6? Yeah, 6. And we're talking about inches. All right, number 6. Find the distance between Centerville and Salem if they are 9 centimeters apart on the map. So this time we're going to have x, what is this, kilometers, and 9 centimeters. And then it says with a scale factor of 1 centimeter to 17 kilometers. So we have 17 kilometers to 1 centimeter. So I look at my x. My x is in the top there. My x is in kilometers. So x kilometers over 17 kilometers equals 9 centimeters over 1 centimeter. To solve this, I'm going to need to multiply by 17. So x equals 9 times 17, which is 9 times 17 equals 153, and we're talking about kilometers. There we are. All right, so those are the 3 different types of problems. Notice that they're kind of grouped up on the front page of the notes. On the homework, they aren't going to be grouped up like this. They're going to be kind of jumbled up. So we have number 1 and number 2 were about shadows. Numbers 3 and 4 were about models. And number 5 and 6 were about maps. So let's look at number 7. A globe that is 2 feet tall casts a shadow that is 5 feet long. So 2 feet tall, 5 feet long. Find the height of a telephone booth if the shadow is 20 feet long. So again, here, if we were to draw on the rest of it, we'd have similar triangles. We start off with our x on top, x height, and the 2 height. 20 shadow, 5 shadow. Oops, no, just 5. So this is x over 2 equals 4, which is x equals 8. And this is dealing with feet. There we are. Number 8, find the distance between Georgetown and Milton if they are 9 inches apart on the map. So we'll say Georgetown and Milton, they are x miles apart. And then on the map, they are 9 inches apart. So then we go and write our scale factor. We have 13 miles to 3 inches. Now to write our proportions, we get x miles over 13 miles equals 9 inches over 3 inches. So this is the same thing as x over 13 equals 3. So x equals 39, and we're dealing with miles. All right. Number 9. A model satellite has a scale factor, or a scale, of 1 centimeter to 3 meters. The real satellite is 12 meters wide. So I'm talking about a 12-meter wide object. 12 meters wide. How wide is the model? The model is going to be x centimeters. And then over here we have our scale of 3 meters to 1 centimeter. So whenever I write my proportions here, I'm going to start with x centimeters over 1 centimeter equals 12 meters over 3 meters. And there we just have to reduce x equals 4, and we're talking about centimeters. All right. Number 10, Salem and Riverside are 64 miles from each other. 64 miles. How far apart would the cities be on a map? So we're going to say x, and then we're talking about inches. And then it says the scale is 16 miles. I guess I should put miles to 2 inches. Now, if you wanted to, before you even started, you could reduce this scale factor. We could see that it would go to 1 to 8. In fact, I'm going to go ahead and write that here. So this is 8 miles to 1 inch. If you didn't want to do it like that, if you didn't want to reduce, it would work out just fine. This just makes the numbers a little bit smaller for me to do in my head. So I'm going to start off with x over 1, x inches to 1 inch is 64 miles to 8 miles. And then here, because we already reduced in the beginning, we're able to just reduce here, and we get x equals 8, and what are we talking about? Inches. There we are. Number 11, an adult elephant casts a 18-foot shadow. So here's 9, here's 18. Oops, I guess 18 should be longer. How tall is a car that casts a 12-foot shadow? Now, if we just look at this, we can probably see that x is going to be 6. I'm going to still write it out. That way, if the problem isn't like this on your homework, you have something to base it off of. But if you see this is 9 and 18, and 9 is half of 18, then x should be half of 12, right? But again, I'm going to write it out just so that we have it. So I'm going to take x height over 9 height equals 12 shadow over 18 shadow. Let's reduce these. We get, actually, I'm just going to multiply the 9 over. So I get x equals 12 times 9 over 18. 9 and 18 I know can cancel, so that gives me 12 over 2, which is 6. And what are we talking about? Miles, feet, feet. We'll talk about the foots. All right, number 12. A model train has a scale of 3 inches, a model train has a scale of 4 inches to 3 feet. If the real train is 12 feet tall, so we'll say 12 feet tall, we want to know how long is the model, or how tall is the model. It's in inches. We'll call it x. And then over here we have 3 feet to 4 inches. Now it's important to also notice what units are they talking about, because here we have 4 to 3, and you might want to say, well, 4 is bigger than 3, 4 should go with the bigger number, right? But that's not the case here, because we're talking about 4 inches and 3 feet. So the 3 has to go with the 12. Let's start off with our x. X inches over 4 inches equals 12 feet over 3 feet. So x equals 12 times 4 over 3. 12 and 3 can cancel to be 4. So I just have 4 times 4, which is 16. And what are we talking about? We're talking about